Hello and welcome back to Complex by Mr. B. In today's video, we'll be focusing on tackling a few multiple choice questions on acids and bases. So let's see how we get along. Now, in question number 1, you're asked to determine the volume of 0.2 molar barium hydroxide that's required to fully neutralize 30 centimeters cubed of 0.1 molar HCl. And we've been given 4 options. Now, let's see if we can begin to eliminate some of these answers before we get started. Because the question tells us we've got 0.1 molar HCl and the concentration of barium hydroxide is 0.2 molar, and that's what we're working out the volume of. The barium hydroxide is double the concentration of HCl, and for the HCl we use the volume of 30 centimeters cubed. So it so follows if barium hydroxide has double volume, double the concentration, its volume must be less than 30 centimeters cubed. So it's not going to be A, it's not going to be B, it's going to be either C or D. Now, which one is it out of the two? Well, if we've got double the concentration of barium hydroxide, then we're going to require half the volume of barium hydroxide to fully neutralize the acid. So that's going to be 15 centimeters cubed. But then we have to also consider that the mole ratios between barium hydroxide and HCl, and in fact, the mole ratios between the two, it's going to be a 1:2 ratio of barium hydroxide to HCl. This means that we're going to half the volume once again, because for every 1 mole of barium hydroxide, we've got 2 moles of HCl. So half the volume again divided by 2, and we're going to end up with 7.5 centimeters cubed. You could alternatively work this out using maths from first principle. So you could start off by working out the moles of HCl. Once you've got the moles of HCl, divided by 2 to work out the moles of barium hydroxide, and then simply work backwards when using the equation N is equal to Vc. If you know the moles of barium hydroxide, you can work out the volume by doing N times C. That's pretty much it there is to it. Right, okay, so question number 2. You're told that in a titration, 0.52 grams of a diprotic acid, so diprotic meaning 2 hydrogens, reacts exactly with 100 centimeters cubed of 0.1 sodium hydroxide, and you're given the equation and it's balanced. You're asked to identify what the acid is, and you've been given a selection of 4 organic acids, each of which are dioic acids. So we need to identify which one it is, and we've been given limited data. We've been given the volume and the concentration of sodium hydroxide. We've been given the mass of H2X. Now, out of the two, the only thing I have been given the most information for is the sodium hydroxide. I've been given the volume and the concentration, so I can work out its moles. So the moles of NaOH is going to equal N is equal to Vc. The volume is 100 times 10 to the minus 3, because we have to convert to decimeters cubed, multiplied by 0.1, and that gives us 100 times 10 to the minus 4 mole. So, if we know the moles of sodium hydroxide, we can work out the moles of the diprotic acid, H2X, because we've been given the ratio. It's in fact for every 1 mole of H2X, we've got 2 moles of NaOH. So to work out the moles of H2X, it's simply going to be half the moles of what we've just calculated. So that's going to be 50 times 10 to the minus 4 mole of H2X. So we know the moles of H2X, and we need to identify the acid, and we've also been given the mass. So we need to use the mass and the moles of the acid to work out its identity. We can do this by using the relationship N is equal to M over Mr, And seeing as we know the mass and the moles, we're going to rearrange this to give us the MR. So M over N. So we've got 0.52 divided by the moles that we've just calculated. No, that's -4, beg your pardon. Okay, let's have a look and stick this into a calculator. That should still be visible. Yeah, okay. So 0.52 divided by, and that's 50 times 10 to the -4, and that equals 104. So we know the MR of that is 104 grams per mole. We're not given the MRs of any of them, but what we are told is each one is a dioic acid. Oic acid representing a carboxylic acid. So we've got ultimately two of the, let's remove this away again. So we know we've got two of these groups ultimately. So let's work out the MR of a single carboxylic acid group. So we've got carbon, which has an MR, has a relative atomic mass of 12. We've got two oxygens, that's 32, 32 plus 12, 44, plus 1, 45. We know we've got two carboxyl groups because it's dioic acid. So it's going to be 2 times 45, that's 90. So we're going to have to subtract 90 from this. That gives us a remaining 14 grams per mole. So out of these, which one is it going to be? Well, we need to identify that if we've got two carboxylic acids, both of which together have a MR of 90, the only possible option is if we've got a carbon in between them with two hydrogens. So we've got 3 carbons in total. So that's going to be propane dioic acid. So it's going to be B for that one. Moving on to question number 3. You're told that a weak acid, remembering that weak acid only partially dissociates, in aqueous solution as shown below. And we can see the partial dissociation from the use of the equilibrium arrows. You're also told the enthalpy change for this, and that's given as a positive value, 20 kilojoules per mole, signifying to us that the forward reaction is endothermic because it's got a positive value. Okay, so which one of the following changes will result in a decrease in the pH of an aqueous solution of the acid? Okay, so if we're asked about a decrease in pH, that means we want something to be more acidic. So if we want something to be more acidic, we know that acids are ultimately a measure of or acidity is ultimately a measure of how many H plus ions we have in solution. So if we want something to be more acidic, we want it to have more H plus ions in solution. If we look at the equilibrium sign, we can see that we've got H plus, and that's on the right hand side. So we want to apply a change to this equilibrium, which is going to cause more H plus ions to be made. In other words, we want the equilibrium position to be shifted to the right hand side in favor of the H plus. So let's have a look at the options we've been given. Addition of a little aqueous sodium hydroxide. Okay, so sodium hydroxide is a base. It's going to introduce OH minus ions to this equilibrium. Well, the OH minus ions are going to react with the H plus. If it reacts with the H plus will actually decrease. We want the H plus ions to increase, so it gives us a more acidic solution. So it's not going to be that. Raising the temperature of the solution. Well, if we raise the temperature for a reaction in equilibrium, it shifts the equilibrium to the end towards the endothermic direction. And in fact, if we increase the temperature, we know the endothermic direction is to the right hand side, as the enthalpy change informs us. So if I increase temperature and the equilibrium shifts to the right hand side, the endothermic direction, that means we're going to make more H plus ions. If we make more H plus ions, then yes, that does indeed mean that we're going to increase the acidity of the solution. So yes, the answer for 3 is indeed B. And moving on to the last question that we've got here, we've been told that for question 4, HA and HB are two strong monobasic acids. So they're strong acids, meaning they fully dissociate. You're told that you're told the volume and the concentration of HA and HB. So that's 25 of HA of concentration 6 molar and 45 centimeters cubed of 3 molar HB. You've been asked in the question, what is the H plus concentration in moles per decimeter cubed in the resulting solution? So to do this, we need to understand a strong acid is one that fully dissociates. So I'm just going to write out an equation to show the full dissociation of the acids HA and HB. So because we know it's a full dissociation, it fully dissociates, we're going to use the non-reversible arrow as shown, and I'm going to do the same thing for HB. So we've got HB dissociates fully to form H plus and B minus ions. So let's have a look. We know the volume and the concentration of HA and the volume and concentration of HB. What can we do with that information? Well, as ever, work at the moles. So if I do this to begin with for HA, I'm told that HA has a concentration, sorry, a volume of 25 times 10 to the minus 3 to convert to decimeters cubed, multiplied by the concentration, which is 6. So we know the moles of HA is equal to 0.15 mol. Let's do the same thing for HB. We're told that HB has a volume of 45 times 10 to the minus 3 in decimeters cubed, multiplied by 3. And we've got 0.135 mol. Okay, so we know the moles of HA and HB. Now we're asked to work out what is the H plus ion concentration in moles per decimeter cubed of the resulting solution. Well, here we're going to use the equation. If we know that each one is a strong monobasic acid, meaning each one only has a single hydrogen to donate. As we know that we know that acids are proton donors. So if we've got 0.15 moles of HA, it so follows we've got 0.15 mole of H plus according to that equation, because it fully dissociates. And in the same way, because all the HB also fully dissociates, we've got 0.135 moles of H plus from the dissociation of that acid. So what is the H plus ion concentration? Well, let's sum the two moles together. So we've got 0.285 moles of H plus in total, 0.285 moles of H plus in total. We want to work out the concentration though, and we know that N is equal to Vc, so therefore concentration is equal to N over V. We need to do the moles, which is 0.285, divided by the total volume. And now the total volume is, in this case, 25 centimeters cubed plus 45 centimeters cubed, so that's 70 centimeters cubed. So if we do this, divided by 70 times 10 to the minus 3, excuse my appalling handwriting there. So 0.285 divided by 70 times 10 to the minus 3. There we go, and that's equal to 4.07 moles per decimeter cubed. So which answer matches up most close to that? Well, it's not 1.9, it's not that, it's clearly C. So that's our answer there. Okay, I hope this was useful in terms of applying good exam technique to multiple choice questions. Until next time, bye.